Hello and welcome to Lesson 4 of Python for Musicians, a Python tutorial series aimed at musicians of all levels. In the last lesson, we looked at how to work with audio files in Python and synthesized some synth sounds using sine waves. Today we'll be expanding on this, creating different types of wave shapes to use as the basis for our sounds and even perhaps as modulators. We'll be jumping straight into Python today. We'll first look at creating sawtooth waves and introduce the notion of a phaser, which will act as the fundamental oscillator building block. We'll then look at creating triangle waves and square waves while checking out two ways of doing pulse width modulation. At the end, we'll combine everything into a list of functions to smooth out any small-scale projects that you may want to use these in. I encourage you to follow along with me, typing out the code as we go to build a habit of coding these things, especially if you're new to Python. As usual, I've documented the whole lesson into a GitHub repository, which you can find in the description for you to use later on. Let's jump into Python. I've gone ahead and done the usual steps that we do in this series. I've created a Lesson 4 directory inside our Python for Musicians file, and I've activated our Python for Musicians conda environment. I've created a file in here called waveshapes.py, and I've gone ahead and imported numpy as np to do all our math processing. I've imported matplotlib.pyplot so that we can plot some of our waveforms to see how they look. I've also imported soundfile so that we can export our sound from Python into our computer so that we can give them a listen. I also defined some audio settings that we'll be using. So sample rate equals 44,100 Hz, that's standard CD quality. And the sound files that we'll be generating are going to be 5 seconds long. I went and created our time array as well. I covered creating this time array in the last lesson, so if this is new to you, do refer to the last lesson to see exactly how this time array has come about. In this lesson, we're going to be creating our wave shapes by molding our time arrays into those wave shapes. We're going to start with the sawtooth wave. The sawtooth wave is often the default patch on most synthesizers. Their name comes from their waveform because it does look a bit like a saw blade. It's generally very buzzy as a sound, and you'll see now that when we do it digitally, it's going to be even more buzzy. And the reason it's buzzy is because of the sharp corners that it has. To get to the sawtooth, we're going to go through an intermediary function known as the phaser. The phaser and the sawtooth are almost identical, except for one detail. The sawtooth is an audio wave, and so needs to be centered around 0. So the values will go from -1 to 1, or if scaled, it will be between minus gain to plus gain, whereby the phaser always goes from 0 to 1. The phaser is not meant to be an audio wave. It is meant to be an indication of where in the oscillator cycle we are at. So a phase of 0 means that we are at the very start of the waveform. A phase of 0.5 means we are exactly halfway through our waveform. And a phase of 1 means we are at the end of our waveform or the new beginning of our next waveform. We'll be building the other oscillator wave shapes based on our phaser as well. But we're starting with the sawtooth because it's merely a scaling problem. Let's define some oscillator settings. Let's use a wave frequency of 200 Hz and a gain of 0.2. I'm going to create a temporary array called modified time array that we will use to plot so that we can see the progress on our development. Modified time array, and for now it's going to be just the time array, nothing crazy. To plot it, we will simply use plt.plot and then time array as the x-axis and modified time array on the y-axis. And we need to show the graph. Let's start here and see what we're dealing with. So this is what we've got. We've got a line that goes from 0 to 5 in 5 seconds. So how can we shape this linearly going up line into a line that goes up to 1 and then goes back to 0 to then go back to 1 and then cuts back to 0. Thankfully for us, NumPy has a function called modf, which will return the decimal part of every number in an array. So if we gave it a list of numbers that went from 0 to 5, it's going to give us only the decimal parts. So from 0 to 1, it's going to not change anything. But then from 1 to 2, it's going to go back from 0 to 1. So let's put this function in action. np.modf, open brackets, and then we'll put our time array in there. And one thing to note is that modf actually returns a tuple, the first element of which is the decimal part, but the second element of which is actually the integral part. We don't really care for that second part. So because it's a tuple, we can say we just want the first element. So that would be element 0. Let's plot this now and see what we're working with. This is already looking much better. It goes from 0 to 1, and then cuts back to 0, and then goes back to 1. And it does this once every second. So we now have a shape that essentially repeats once every second. It has a frequency of 1 second. So if we want to get this function to repeat frequency times per second, we need to multiply our time array by frequency. So in here, if we multiply this by the wave frequency that we wish, and then rerun, it's going to look like a bit of a mess, but if we zoom in, it will make sense. So let's zoom in now to this portion over here, very small portion, and we'll see that it kind of looks like what we are expecting to see. It goes from 0 to 1 many times. So believe it or not, that was all we needed to do to get our phasor. We just created a ramp function that goes linearly from 0 to 1, wave frequency number of times per second. So instead of modified time array now, I'm going to call this phasor. And now all we have to do to get our sawtooth wave is to scale it to the right range. Let's create our sawtooth wave, and it's essentially the phasor. We need to multiply it by 2, and then by subtracting 1, what we've essentially done is stretched out the phasor from being in range 0 to 1 to being in range -1 to 1. For demonstration purposes, I'm going to go ahead and make the time in seconds equal to 0.05 and plot the sawtooth wave, just so that we can see the range difference. So yep, it goes from -1 to 1. And then finally, all we really need to do is to multiply the entire thing by the gain that we have specified above. So plotting this now should show us what we expect to see. A waveform that goes from -0.20 to +0.20, exactly 200 times per second. Before we listen to this sawtooth wave, there are 2 rules that we have to respect when we're creating audio files and listening to them in Python. These rules were introduced in lesson 3, and I'm going to state them again now because they are extremely important. The first rule is never, ever listen to something you have written in Python with headphones on, because you don't know if something went wrong in your code, and if something did, it might really hurt your ears. The second rule is to see whether your output is clipping, and if it does clip, to not actually write the file. We've written a function for this in the last lesson, and we called it sanity check, and I'm going to paste it at the top of our file here. Let's change the time back to be 5 seconds now. Let's toss our sawtooth wave inside our sanity check function, and only after our sanity check are we going to write the sawtooth wave into an audio file. So soundfile.write, again we covered this in the last lesson. We're going to give it a name, sawtoothwave.wav. The file that we are writing is the sawtooth wave variable, and it has a sample rate that we have defined above here. We don't need to plot this, so I'm going to comment this entire section out, save and run. And now you should see in our folder, we have a wave file called sawtooth.wave. This is what that file should sound like. Amazing. Let's now get from our phasor to a triangle wave. Let's clean the canvas a bit. I'm going to delete this sawtooth section here and actually call it triangle. As we are working from our phasor, I'm going to define our triangle to be just the default phasor for now, and then repeat what we did with the sawtooth wave by plotting and seeing if we are doing the things correctly. So let's plot our triangle wave, changing the time in seconds again to being 0.05 so that we can see a zoomed in view of our waveform. This is the phasor that we're working with. Now, the core difference between the sawtooth wave and the triangle wave is essentially the angle of slope that goes back down from 1 to 0. In the sawtooth wave, it's essentially a direct cut. So once it reaches a number that's past 1, straight back down to 0. But the triangle wave needs to go up and down at about the exact same rate. Now again, there are many ways to do this, but my personal favorite way to do this is to fold the phasor in on itself. One way to fold the waveform in this way is to use the NumPy fabs function. What fabs does is it takes any negative number and essentially makes it positive. So to use that to our advantage, if we can scale the phaser to dip half of it below 0, then tossing that whole thing inside the fabs should flip the bottom half up. From there, we can just scale our function back into the range that we need to create our triangle wave. So to dip the bottom half of our phaser below 0 is essentially exactly what we did with the sawtooth wave. So let's create our sawtooth wave over here. So we multiply the phaser by 2 and then subtract 1 and then toss this whole thing inside the NumPy fabs function. So np.fabs. Let's plot this to see where we're at. So as we expected, the values are entirely positive from 0 to 1, except it has a slope down and then a slope back up and a slope down and a slope back up. And so all we really need to do now is, again, to multiply by 2 and then bring it down by 1. So let's do that over here. Multiply by 2 and then subtract 1. This operation should get it in the range -1 to 1. So to get it to the necessary gain, we multiply the entire thing by the gain that we want. So gain multiplied by that entire thing. Let's plot it to make sure. And here we go. Here's our triangle function. It goes from positive 0.20 to negative 0.20 in our classic triangle fashion. So let's sanity check our triangle function now and write it out as a triangle wave.wav. We give it our triangle function, and then we save, and then we don't care to plot it anymore, so we can comment that out. Let's run it. Perfect, no errors. And then if we list our items, we should have in our directory a new file called trianglewave.wav. Let's listen to it. Amazing. Let's now look at the square wave. Square waves, or pulse waves as they're also known, are waves that look like squares. In typical synthesizers, you can also change the pulse width, so that's how long it stays up compared to how long it stays down. We'll start by looking at how to make just a basic square wave with half down, half up, and then look at 2 ways to making that pulse width modulation. Let's reset our workspace. And let's once again start with our square wave just being our phaser. So how do we get from our phaser to a square wave, where it starts at the bottom and then jumps magically at the top? Again, there are many ways that we can think about doing this, but the way that I normally do it is that I round the phaser to either 0 or 1, depending on where it is. So if we rounded our entire phaser function, all the values that are under 0.5 are going to be 0, and all the numbers that are above 0.5 are going to be at 1. That's the basis of our square wave, and then all we have to do is scale it from there. So let's implement that. Let's use NumPy's round function to round our phaser, and then, of course, just scale it back down from the range 0 to 1 to -1 to 1. And then directly from that range, let's rescale the entire thing by the gain that we want to use. Let's replot this and see what we have. I think this pretty much looks like a square wave to me, from -0.2 to all the way to positive 0.2. And it has an equal amount of down to up. And that's what we're looking to change with our pulse width amount. So as you can probably guess, the way to change the pulse width is to do some mathematical trickery to our phaser before it goes into the round function. One way that works is to simply add a constant to our phaser. As long as that constant is in between -0.5 to 0.5, this should still work. Let's see why that works. Let's remove the gain and the extra scaling to show this best. Let's start by adding a constant of 0.2 and see what happens. So you can see that it's spending more time at the top here than it is at the bottom. And if instead of 0.2 we put 0.4, you'll see that that effect amplifies even more. If we were to remove 0.4, we should hope to see the opposite effect happen. But what happens if we add more than 0.5? Plus 0.6? That looks suspiciously like our minus 0.4 step, except that the range now of our wave here goes from 1 to 2. Before it was going from 0 to 1, and now it's going from 1 to 2. And that's because our phaser, when it initially started at 0, it would still round to 0. Except that now that we've added 0.6 to the entire thing, 0 plus 0.6 now doesn't round down to 0 anymore. It actually rounds down to 1. Now this method of adding a constant to our phaser works fine for pulse waves, especially if we put a check inside that makes sure that the added pulse width is in the desired range. But there's another way that we can do pulse width that actually also works with other wave shapes. That way of doing this is, instead of adding a small constant before we round, what happens if we put an exponent to that phaser before we round? So let's, in this case, give it an exponent of 2 and see what happens. You'll notice we have also created a form of pulse width. And I think it's easier to see why this is if we also plot the phaser on top of this. You'll see now that our phaser is actually getting skewed on its way up. So it's only getting rounded once our scaled phaser is going above 0.5. Now this mathematical trick of adding an exponent to our phaser only works because our phaser is in the range 0 to 1. As long as the phaser is in the range 0 to 1, any exponent that we give it is going to also be in the range 0 to 1. And if we want to add a degree of control to this pulse width, we essentially need to figure out at what point does our ramping up phaser cross the 0.5. So for convenience, I've gone ahead and created a wave frequency of 1, just so that we can try and think through this problem a bit. I know that there are better ways to do math on YouTube, but this way was quick, and I think it gets the job done. We want to figure out the exponent at the particular pulse width number that will give us a number of 0.5. So if we wanted a pulse width of 0.5, at 0.5, what is the exponent of 0.5 that will give us 0.5? That's just 1, right? But when we start going to the other edges, it starts to get a little messy. So how do we solve this equation? First step is to take the log of both sides. So we take the log of pulse width to the function and we equate that to the log of 0.5. And then there's a very neat log property which says that you can take out the exponent inside the log and multiply it by the log itself. So this identity works, and we do this. And then finally, this gives us that the function of the pulse width is equal to log 0.5 divided by log of the pulse width that we want. So let's write this function in Python now. Up here at the top, we are going to define a function, and we're going to call it pulse width to exponent. It's going to take in a pulse width of type float. And if we don't specify a number in here, we want it to assume that it's going to be 0.5. So essentially default pulse width. This function is going to return a float. There are two things that we need to make sure of. We essentially need to make sure that the pulse width given is in the range 0 to 1. And it needs to be a hard limit, because if it's 0 or if it is 1, the resulting phaser is going to be a straight line, either at 0 or at 1, and that's not ideal. So let's assert that pulse width is more than 0 and give an error message. The pulse width needs to be greater than 0, and another condition that the pulse width needs to be less than 1. Finally, we want to return the numpy.log of 0.5 divided by the log of the pulse width. Now in here, instead of phaser to the power of 2, we want phaser to the power of pulse width to exp, and here we'll give it a pulse width number. So in oscillator settings, let's give it a pulse width of 0.85. Let's fix our frequency to be back to 200 Hertz. Let's make our wave 5 seconds long. And then the last thing we need to do is scale our entire square wave back into the desired range of minus gain to plus gain. So let's activate our sanity check now on the square wave. Let's write out the file after the sanity check to be square wave. Let's give it the square wave function that we have just created, and let's comment out the plots because we don't want them. Let's run our script, and then let's list our items. And here we go. We have our squarewave.wav, and I will play it for you now. So now that we have looked at all the functions, including the sine wave in the last episode, we can now think about bundling them up into their own code bubbles, also known as functions. Now, we're not going to get into extreme detail here because I don't think that using these functions is perhaps the best way of making these oscillators. I think they're much better done as classes, and we will look at classes in the next few episodes, but I still think it's worth doing. So our plan is going to be to create 5 functions. The first one is going to be make phasor, which takes in a time array and then returns a phasor. The next 4 functions are going to take in that phasor and adapt it to be the desired wave shape. So let's start here with defining make phasor. It will take in a time array. As per our best practices, we'll be using type annotations in function definitions just so that our code can give us error messages in case we have messed up somewhere. So the time array is going to be of type numpy nd array. And the phasor also is going to need a frequency value, which is going to be a float. This make phasor function is going to create a phasor, which is also of type np.nd array. Now we already have the equation for this phasor. We've been using it this whole lesson. So let's just copy it from down here, write return, and paste that in. And we just need to double check that the variables in here match those that are given in the function definition. So here, instead of wave frequency, it should just be frequency. Let's make our sawtooth with mk sawtooth. It's going to need to take in our phasor, which again is of type np.nd array. We can give it a pulse width of type float, and we'll give it a default value of 0.5. And we can also define a gain straight in here. Again, type float, default value of 0.2 this time. The sawtooth will be returning another nd array. While we're here, let's go ahead and actually copy our entire function definition and create it another 3 times, because most of the wave shapes will be taking in the exact same parameters. So after the sawtooth, let's define our triangle, and then our square, and then finally our sine wave. We saw earlier that all the sawtooth has to do is just rescale the phasor. Let's incorporate this pulse width here into the phasor. So we give it an exponent of pulse width to exp, and then toss in our pulse width in here. And the order of operations here should be phasor to the pulse width times 2 minus 1, and that's what we expect. Moving on to our triangle, this is the expression that we had come up with before. And once again, we can incorporate the pulse width by giving this an exponent of pulse width to exp of that pulse width. And again, in here, the order of operations should be phasor to the pulse width times 2 minus 1 inside the fabs function, and then the whole thing times 2 minus 1, and then multiplied by the gain. For our square function, we can copy down the expression that we have just created down here at the bottom. And then for our sine wave, the expression we need is this. So inside our sine function, we give it 2 pi times the phasor, because the phasor is time times frequency. And then we can scale our phasor with our pulse width expression. Just to double check that we're doing the right order of operations, let's put all of this inside brackets. To show this off now, let's create a chord where every note in that chord is of a different wave shape. Let's delete our oscillator settings, our phasor, and our square wave now, because we don't really need them anymore. And let's start creating our wave shapes. Sine waves are a good all-rounder. I personally like them to give an extra punch to the bass. So I'm going to give my bass note a wave shape of a sine frequency. I'm going to call it sine for now, badly named, but it's fine. It's going to be make sine. In the phasor section, we need to give it a phasor, which we can make straight within the sine function. So make phasor. And then in here, we need to give it our time array and our frequency. I want to use an A, so I'm going to give it a frequency of 110. And I don't care to give it either a pulse width or a gain, because the default values will work fine for me. Let's create now a square wave an octave up. So square is going to be make square, make phasor, time array, and the frequency now is going to be 220. That's an octave up. And let's give this a slight skew in the pulse width with a value of 0.6. Let's now create a sawtooth wave a fifth above our square. So sawtooth is equal to make sawtooth make phasor. Then we need to give it again our time array, and the frequency of that is going to be 330. So now we're at the E above middle C, and I'm going to bring the gain down for this sawtooth ever so slightly. So the default is 0.2. Let's give this 0.16. Finally, let's give it a ringing C sharp as a triangle wave. So triangle wave is going to be make triangle, make phasor, our time array. That ringing C sharp is going to have a frequency of 550 Hertz. And just for the fun of it, let's skew this as well with a pulse width of, let's do 0.7. So let's build up our chord now. Chord is going to be equal to the sine, and because we're just putting them on top of each other, we can simply add them up. Sine plus square plus sawtooth plus triangle. Now we might get some phasing issues because we are doing pure digital emulation of all of this. So it could be an idea to add some extra movement by adding slight inconsistencies in our frequency. So I'm just going to go ahead and add a little bit of offset to these frequencies. So 220.02, 330, let's make this 329.9, and let's leave this triangle as is. Lastly, let's sanity check our chord before exporting it, and then let's export it. It's going to be an A major chord. Let's give it a WAV extension, and let's give it the chord array to use. Let's save this and run it, and let's listen to it. I think that sounded awesome. Another cool trick that we can do now that we've simplified our wave shapes into these functions is to do ring modulation and create more complicated wave shapes by multiplying two or more different shapes. So for the sake of example, I'm going to keep our triangle and our square wave, and I'm going to give them both the same frequency of 550. Let's introduce some further movement by adding a tiny constant over here. And instead of a chord now, this is going to be a ring mod signal, and it's going to be our square times our triangle. You know what's a cool thing we can do actually? Let's change the pulse widths a bit. So let's keep our square at 0.6, but let's make this triangle skew to the other side with 0.2. Let's sanity check our ring mod. Let's output the ring mod, and let's call it ring mod. Let's save and run again, and let's listen to it. That sounded super digital and very ringy, but it was definitely an A sharp. But I think it sounded cool, and maybe with some filtering it could be even cooler. Now would be also actually a good time to talk about aliasing. So because these wave shapes we're creating are purely digital and are looking like the wave shapes in the exact mathematical way, we're getting this effect called aliasing. Now, aliasing doesn't happen when we're using analog gear and can be avoided in digital systems. Without going into too much detail, what aliasing is when frequencies get too high to be representable by our sample rate, they start being represented in the opposite direction. And this happens mainly with waves that have high harmonics. And I'll show an example now where I'll take a sawtooth wave and go from low frequency to high frequency, and you'll see what I mean. The way I like to explain aliasing is by using this comparison. So have you ever noticed how when you're in a car and you're looking at the other car that's driving next to you, you look at the wheel, and when it's driving slowly, it's going forward in the direction that it should be turning to. But then when it starts going faster and faster, at some point it looks like the wheel stops turning and then starts turning in the opposite direction. That's because your brain's frame rate, if you will, runs slower than how fast the wheel is going. So every time your brain is taking a frame to understand what it's seeing, the wheel has moved so much that it actually looks like it's moved backwards. So for demonstration purposes, let's bring back our sawtooth friend and let's give it a frequency that goes forward. So let's create a frequency array, and we're going to use linspace for that. Let's have it start at 200 Hertz and go up to about 1500 Hertz. For our math to work out, it needs to have the same number of samples as our time array. So let's just use that again. And here it doesn't matter if our endpoint is true or false. Two more things we need to do. We need to give our frequency array inside the make phasor equation. And because we have used type annotation up here, make phasor is expecting a float and we've given it an ND array. So we can change that back to being NP ND array. And this should now all be working. Let's sanity check our sawtooth. And let's print it out, and let's give it a name, varying sawtooth. Let's run this and listen. There it is. Did you hear it at the end, how it started going meow, 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 meow? So that's aliasing. And we will be looking at ways to reduce that in future lessons. What we saw today was one way of creating the classic oscillator wave shapes based on phasors. This is of course not the only way to be creating these shapes. The benefit of this way of creating is that NumPy is optimized to do these operations very, very fast. The downside is that we are creating whole blocks of audio at once. You can perhaps see why this could be a problem in a live environment, again depending on how we use them. In the synthesizer that we're working up to building, these oscillators will need to be optimized by using classes. I'll introduce classes in the next lesson. If you know anyone who would benefit from this series, please share it with them. Also, if there's a topic that you'd like to see covered, or if the level is too advanced or simple, let me know in the comments. And if you'd like to follow the series and support the channel, consider leaving a like and subscribing to receive the rest of the lessons in your feed. I'll see you next time.